Hello everyone, in this video I'm going to show you how to do grid independent tests in numerical simulations, being efficient in terms of computational time and having accurate results are both equally important. However, if you try to have a very high accuracy in the results, that will compromise on the efficiency time. So in order to compromise between these two, getting a high accurate results at the same time being efficient, so we need to conduct grid independent tests. So GIT is basically a process where at one point the grid size or the mesh size has minimal impact on the results. So in this video, I'm going to show you how the GIT can be done manually without using parameter set. I'm using Fluent to remove that. Okay, and I'm going to design the geometry using design modeler. And I'm going to design a small diameter of a cylinder with a diameter of 93.4 mm, but it's a very long one, it's 6 meters. So I'm choose XY plane as my sketch plane, and I click the Z direction axis here so that my plane will become like that. Go to sketching tab, and I'm going to zoom in until it goes to a very small value. All right, about that. Click circle. Make sure that when you try start sketch, the capital P appears. Then you can click and drag. Then click dimension. Choose diameter. Click the edge of the circle. Show D1 here, so you go to D1. I'm going to change that to 0.0934 because I'm using a meter as the unit. So got that sketch already. So go to extrude, choose sketch 1, apply, change the depth to 6 meter, enter, and generate. So there you go. We have a very long cylinder or a rod. Okay, done with that. So now we go back to workbench. Now the symbol here has changed to green mark here. So it means that it's good, and we can proceed to mesh. The double click mesh. All right, so this is the mesh window. So go to mesh, right click, insert, sizing. And I'm going to choose the edge here. So make sure that the filter, the edge is selected. Okay, choose that, apply. There are many ways to do this. Either you can change the element size, but in this case, I'm going to use a number of division because of the geometry is simple that way. So I'm going to change to 10 and generate. Okay, we got that. All right. Next, I'm going to go for name selection. So I choose the face, select face, and then go to that face here. Right click, click name selection, and put inlet. And then click the whole wall here. That's going to be a wall. And on the end of the cylinder, that's going to be the output. Sorry, the outlet. All right, so we got that. Okay, so basically we're done with mesh. Now go back to workbench. Right click, update. All right, done. Just going to save this first. Okay, now we go for Fluent, double click setup. Okay, so this is going to be 3D. Choose double precision and click OK. All right, so we got that. All right, everything done. So the first thing that we need to do is to um, check the mesh. Okay, the most important thing is you look at the volume here and make sure that there is no negative volumes. So that one is okay. All right, so going to maintain that pressure base, absolute and steady. For the model, for the turbulence model, I'm going to choose K epsilon, realizable. Okay, that one done. For material, go to fluids. I'm going to change instead of air, that's going to be water liquid. So go to Fluent database and scroll down. There's a water liquid there. You just maintain all the properties and copy. Then you see that now there is a water liquid under fluids. So closed and closed. And for cell zone condition, the default one is air. So make sure that we assign the water liquid as a material. So change that. Okay. Okay, for boundary condition, the inlet, that inlet's going to have a velocity of 1.823. Okay. And then the outlet, the pressure, that's going to be 60,000. Okay, and the rest maintain. Got that. And for method, for the interpolation method, change everything to become a second order upwind. Okay. And for monitors, for the residual value, we're going to change the absolute criteria to be 10 to -4. Okay. Okay, done with that. Then we can initialize. So click initialize. So the initialization is done. So we can click run calculations. Just press a check case, make sure that everything is fine. So no recommendation, no error. So good, okay. Then for number of iteration, I'm going to put 250 here. And we calculate. Okay, now calculation is complete. So double check this. So make sure that there is a statement shown here, solution is converged. So even though if your calculation is complete, but the statement is not appear, so you need to add the number of iterations until the solution is converged statement appear. So that one is good. So next is I'm going to analyze on the results. So in GIT, basically try to get at least more than one parameter to double confirm on the results and not only one. Okay, so I have prepared a spreadsheet which has the division number from the mesh, the node number, and I choose two parameters here, which is the average velocity and the maximum velocity. Okay, so I go back to mesh just now. and then click Mesh, go to Statistic. There's a nodes number and elements number. So I'm just going to copy the nodes number here and put that in my spreadsheet. Okay. And to analyze the results, I'm going to use CFD post. I'm going to save this first. Okay, double click results. All right, so now you can see a wireframe of the inlet and then a wireframe of the outlet there. So now I'm going to create a plane which is 0.7 meter away from the outlet. Why I choose this plane is because I have an experimental data, which later I can compare the result with the experimental data. So location, plane, let's choose that plane 1. The method XY plane and 0.7 meter. Then click apply. Okay, all right, need to check that. So there, the plane. Okay. So this plane is 0.7 from the outlet. Next is I'm going to create a point, which that point is at the center of the plane 1. Okay, so X, this is represent X coordinate, Y coordinate, and Z coordinate, and the Z coordinate going to be 0.7. Apply. You have the point there. Okay, and next is we're going to get the value of the average velocity on the plane and also the maximum value of velocity at the center point there. So go to calculators, function calculator, area, choose area average, location, choose plane 1, and calculate the results. Oh, sorry. Yeah, the variable there changed to velocity, calculate. So copy that number and paste that to our spreadsheet here. Okay. Next is I'm going to choose maximum value, location at point 1, variable velocity, calculate. So now I have this number. So highlight, copy, and then paste in the spreadsheet. So there you got that. All right. So we've done with the first size or the division. So I'm going to name this as D10 represent the 10 number of division. The number of division is 10. Okay, I'm just going to close all this to save that first. Okay, I'm going to close all this window here. So now I'm going to reduce the number of division from 10 to 20. And what I can do is click that small arrow there and click duplicate. So basically all the data from this block A here are already the same as in block B. I'm going to rename this as D20. Okay, geometry the same, so I'm going just to change the mesh. So double click mesh. All right, go to mesh, expand this, go to edge sizing, and for number of division from 10, I'm going to change that to 20 and generate. Now you can see there's a smaller mesh there. Okay, and go to statistic and choose that number. All right, basically it has the same notes number there. All right. Okay, let's see if you do 30 and generate. You can see it becomes smaller there, and the statistics now become higher. The notes number is higher. But for this case, I'm just going to maintain that to 20 first. Okay, generate again. Make sure don't forget to generate. All right. So we close this. Right click, update. Okay, now I'm going to open Fluent. Double click Setup. Yes. Okay. All right. Check volume. Okay, so you can see the material. So we have this water, liquid, everything. So cell zone, go to boundary. It's a water, liquid. So basically all that we have set in block A just now, everything is here. Don't have to worry. So we just go direct to initialization, initialize it. Okay, done. And we are going to run this again. I'm going to set 250 as well. Okay, just check case. All right. And calculate. All right, the calculation is complete and the solution is converged at 228 iterations. Okay, good. So we go back to Workbench. Just going to save this. Okay, I'm going to open up CFD post and get the value for the average velocity at 0.1 and also the maximum velocity at 0.1. So straight away go to calculators, function calculator, area average, plane 1 velocity, calculate, and highlight and copy the value. Then we go for maximum velocity, 0.1, and you get that value and paste here. Okay. It has the same value because I think we've got a number of nodes, not no change. It's okay. So we close this. Also close Fluent as well. Okay, so we repeat the same step here. Duplicate, and now we're going to increase further the number of divisions. So I'm going to increase the number of division. We have done these two, so I'm going to do 30, 40, and 50. So it means that I'm going to duplicate for another, this one is 30, and another two for 40 and 50. So I'm going to just rename this as D30. All right. So you just change the mesh to the number of division and then run it again and then get the results. All right, so I have done D30, D40, and also D50, and all those results I put it in the spreadsheet. So you can see here the x-axis represent the number of nodes, and the y-axis represent the parameter. In this case, is the average velocity, and this one is the maximum velocity. So you can see that the average velocity has no change, which is makes sense because the diameter of the pipe is very small, and we are taking the average of it. So there's no much change, or it's actually similar for all the number of nodes or the division number. That's why it's very important in GID that you have more than one parameter to compare with. If you look at the maximum velocity at 0.1, and you can see there is a big jump from division number 10 and 20, which has a similar values here. But if you go to 30, which has a nodes number to 99,000 approximately, let's go there, and then go to 40 divisions. There is a big change, quite a big change also here, but not as big as this. And at 50, you can see that the change is no longer significant. It means that you can take these points, which is at the D40 here, the division number 40 with this nodes number as your grid size or your mesh size, because the subsequent results here, the D50, the changes is not that big. Okay, that's how you can do a GID. Thank you.